Well, hello there. I'm Venkatesh. Today's topic is on Fibonacci numbers and its application and golden ratio. So, firstly, Fibonacci number was first discovered by the man named Leonardo Pisano, whose nickname was Fibonacci. Fibonacci sequence is a sequence which each term is the sum of number which is preceding it. Uh, okay. Fibonacci number are defined by recurrence relation defined by the equation which is by an equation which is fn equal to fn minus 1 plus fn minus 2, where for all n is greater than or equal to 3, where f1 is equal to 1 and f2 is equal to 1 as well. So the Fibonacci sequence will be 1, 1, 2, 3, 5, 8, 13, 21, 30, well, I'll write here 34, 55 and 89, so on. The most common experiment of Fibonacci number is with a rabbit, which we have learned in our classes. That is a young pair of rabbits in one of the set is placed in an island. A pair of rabbit does not breed until they are 2 months old. After they are 2 months old, each pair of rabbit produces another pair each month. So the recurrence relation of the number of pair of rabbits on an island in nth month is we can write the recurrence relation. The sequence of recurrence relation is represented by this recurrence relation. So here we can say that this recurrence relation is which follows the rabbit principle, no, rabbit experiment, sorry. Hence, by that we will directly jump to the Fibonacci sequence applications. Fibonacci sequence in nature, actually we can see Fibonacci sequence in nature very much. On the head of a sunflower, we can see the spikes of that sunflower, which are packed so that it can protect its seeds. The packing is also follows the Fibonacci sequence, which prevents the seeds of sunflower from crowding outwards. The petal of sunflower is once again the same plant of sunflower. It may also relate to the Fibonacci sequence. Now let's directly go to the petals. Some petals of flowers relate to Fibonacci sequence or a Fibonacci number. For example, I have collected some of the I think it's visible. I have collected some of the examples for our convenience. 1, 3, 5, 8, 13, 21, 34, 55, 89, all these are Fibonacci number. If we take one petal, the flower which has one petal is white Kelly lily, which has one petal, and three petals is iris. Iris is a very popular flower, and five petal is buttercup, and the list goes on. I think it's visible. The list goes on for this. So let's go to spirals directly. The Fibonacci numbers are found in an arrangement of seeds on the flower's head. There are 55 spirals and spiral rings and 34 spiral inverts of sunflower and daisy flower. Uh, it's a rough diagram. If this is a sunflower spiral, there are seeds inside it. Even this follows Fibonacci sequence as well. Yeah, we have seen pine cone. I think it's a popular one, most common one. Pine cone clearly shows the Fibonacci spirals. Fibonacci spirals can also be found in cauliflower, which we use daily basis. A Fibonacci number can also be found in pineapples, banana. If we slice the banana, there are flat sides, 3 or 4 flat sides. Uh, Pineapple scales have Fibonacci spirals in the set of 8, 13, 12. Well, Fibonacci spirals are also found in various fields associated with the nature, which is it is seen in snail. Just a minute. If we see the structure, it is quite similar to the snail structure, I believe. It's visible. It is quite similar to snail structure. There are many which follows Fibonacci sequence, Fibonacci series in the way of waves. It may be the combination of flowers, sorry, colors, and many things in nature. Let's go to human. Uh, if we go to human organ, to be precisely, every man has two hand. Each one has 5 fingers, and which has we can see 5 fingers, and each one has 5 fingers, and we can see the knuckles as well, uh, which all are in a pattern or a sequence which follows an sequence. Every man has 2 hands, where 2 is a Fibonacci number, and each one has 5 fingers, where 5 is a Fibonacci number. Each finger has 3 parts. Just a minute. You can see each finger has a 3 part. Well, I'll place it. Each finger has a 3 part which are separated by 2 knuckles. You can see 2 knuckles. All are in a set of sequence. If we have a small diagram of a knuckle, you can see it is in order of a sequence. It is in a Fibonacci sequence. So, if we part our the whole finger, we get from here to here. We get these 4 things. We can see all are in a 8, 5, 3, 2 ratio. So this is also an pattern of Fibonacci sequence. If we still go deeper, we can see 5 sense organs, which are also a Fibonacci number, and we have a pair of eyes, again a Fibonacci. It is also a Fibonacci, and pair of ears, pair of legs, pair of hands. Everything follows Fibonacci sequence, and well, when it comes to mammals, if we take mammals, all mammals are pentadactyl, which means that their locomotion is dependent on 5 fingers. For example, if we take a man, his legs has a his leg is a pentadactyl, and if we take the fin of an whale, once again it is a pentadactyl. If we take the claws of tiger, which is again a pentadactyl, they are all these are pentadactyl, which means 5 in number. Their locomotion is in 5 in number. All this also an example of Fibonacci sequence, and I think we will continue this Fibonacci after golden ratio. Let's take up the topic of golden ratio. Well, let us take a line segment. Let's call it as A and well, not here, A and B. Let's take a line segment so that the ratio of A to B is equal to the ratio of the sum of these two, which is longer side. Let us write A is longer divided by B, which is quite smaller compared to A, which is equal to sum of these two by the longer side. And let us call this as 5. Now that's what golden ratio is defined as. Okay, so this can be written as A by A plus B by A, and then A by A is nothing but 1, so I'll write it down. A by A is equal to B by A, which is equal to 5. So B by A is nothing but B by A is equal to inverse of pi, inverse of 5 actually. We can write this as 1 plus 1 by 5. Let's take this as an equation. We call this equation as a star. Okay, now let us substitute 5 in 5, that is I'll write it down. 5 is equal to 1 plus 1 over 1 plus 1 over 5 actually. So we know the value of 5, so let's substitute those. 1 by 1 by 1 plus 1 by 1 over 5. Once again we know the value of 5, and this goes on and on and on. Well, this is a recurrence relation of a variable where it can be defined by itself. We actually want a value of a 5, right? Let us see exactly the 5. It can be written in a quadratic equation form. It is an easy way to do so. Let us multiply by 5 in this equation. We get 5 square is equal to 5 plus 1, and we call this as equation 1. We call this an equation 1. So value of 5 will be square root of 5 plus 1, or it can be written as 1 plus 5. Again, if we substitute value of 5, we get another recurrence relation, that is 5 is equal to square root of 1 plus square root of 1 plus square root of 1, and goes on and on and on. We need a golden ratio. What exactly the golden ratio? Golden ratio is the ratio of longer side, which I have already written. Golden ratio is that the ratio of longer side to the shorter side is equal to the ratio of the sum of to the longer side. It is a sum to the longer side. So let's rewrite this equation. Let's highlight this. So let's rewrite this equation as 5 square minus 5 minus 1, which is equal to 0. Now let's highlight this. Now it looks like an quadratic equation. Now let's solve this quadratic equation by using Sridhar's formula. Here value of A is equal to 1 and B is equal to minus 1, whereas C is also equal to minus 1. By applying Sridhar's formula, phi is equal to 1 plus or minus square root of 1 plus 4 AC 4 whole divided by 2. Now we care about only positive solutions. Now we want the value of phi, so 5 is equal to 1 plus square root of 5 whole divided by 2. Well, let us solve this equation by using our calculator. We get 1.6180339889. Well, we'll write those. This is nothing but the value of phi. I missed one, I believe. Yes, 03398. So we got the value of 5. Wait a minute. So we got the value of 5. Now let us write its inverse. That is phi is equal to, let's do it as greater phi divided by small phi, which can be 1 over 1.61803398. Well, it's obvious we get 0.1618033, which is nothing but you can see, you can compare these two. The inverse of the number is the decimal remaining, the decimal which is remaining, it is the inverse of this one. So this is the golden ratio. It shows so this is the golden ratio. It shows in every field, in every painting, every music, nature, everywhere. The golden ratio is very famous. The golden ratio is very famous. We can see those in many old architecture. I will give an example for that in later of this video. Let's see, for a geometrical structure, does it holds good? Let's draw a star. I think this can work. So this is a star. Where did I keep my pencil? So this is a star. Let's take the ratio of this line segment, whereas let's take this as a longer part and this as a shorter part. The sum will be this. The sum will be this from here to here. So by this we can say that even it also follows the golden ratio. That is, we get the value 5 is equal to 1.61803 as well. So if we take an example of an pentagon which has sides, this is a pentagon. If we draw a diagonal, this is a diagonal. For a pentagon, the diagonal of a pentagon, the ratio of diagonal, this is the ratio of diagonal to any of the sides. The ratio of the diagonal of any of the sides is once again follows golden ratio, which is 1.61, so on. Even this pentagon follows golden ratio. We can see that in a rectangle as well. If we take the larger side, that is A, and shorter as B, for a rectangle, now the golden ratio, which is A by B, is also equal to 5, that is 1.61. So this is this is all over the place. The golden ratio is all over the place because that makes sense. The cell construction themselves, it is a kind makes sense to be the same at different scales, and the ratio from one scale to the next is maybe the same as constituent ratio. For example, you can see as the famous one, the Leonardo da Vinci's painting in Last Supper, uh, is a great example for golden ratio, which the painting also follows this principle. We can see the outer layer of that painting is golden ratio, which is in a triangle in a shape actually. The size of the model or a structure in that painting, each eyes and nose, let's show this diagram, follows this one, follows this structure. uh, there are many of them which follows this golden ratio. And let's come back to the Fibonacci's application. We can see Pascal triangle. It's a quite famous one. This Pascal triangle follows golden ratio. I will show how. So I have written Pascal triangle. If we take the diagonal sum, we get a Fibonacci number. You can check those things. Let's take the ratio of each number of the Fibonacci sequence. Before it, for an example, let's take 8. Uh, Before that, 5, is it? No, 5 is a Fibonacci number uh, which is actually before 8 in Fibonacci sequence. If we divide this, we get 1.6. Perfect. If we take 5 by 3, we get 1.666. And 13 is a Fibonacci number. Before that it's 8, and we get 1.625. 21 by 13 is also 1.61538. If we go further, that is 34 by 21, which is again equal to 1.61905. I have checked this. You can check in calc as well. We get the same. What exactly is happening is, uh, as we do further and further, we will get nearer to the value of golden ratio, that is 5. Uh, so the phi can be written in this way as well. Now, limit n tends to infinity, phi, fn plus 1 divided by fn, which is equal to 168. 5 exactly. uh, we can keep going. We will get in this manner. Let me complete this. uh, if we go further, we will get nearer to 1.61. So this is all about golden ratio. We can frequently see this uh, golden ratio in natural architecture. Also, it is found in Great Pyramid in Egypt. The perimeter of that pyramid divided by twice of the vertical height is the value of phi as well. That is 1.61. We as now human behavior, they believe that the value of 5 is an answer to the creation of the world, which I actually disagree to this. Many mathematician does so. Now we can say this phi value. We can say Fibonacci. Yeah, we can take an example of Fibonacci number. We can say few follow Fibonacci sequence. That is, how I mentioned sunflower, and I mentioned some of them. You can see this. Some of them follow Fibonacci pattern or a Fibonacci sequence pattern, but not every flower follows that. Not every flower in the world follows Fibonacci number, so that even that holds good for golden ratio as well. Not every structure in this earth follows a golden ratio. And yes, that's all about today, and thank you for listening. This is Venkatesh. Thank you.